Okay, so today I'm going to cover assignment 7 of week 7, assignment 7 basically. So let's directly dive into it. Okay, so the first question is consider the following partial differential equations in which the parameter eta is real. You're told that the parameter eta is real, and we have to identify all the partial differential equations which can be made elliptic with a suitable choice of eta. So firstly, what is elliptic partial differential equation? That's what we start with. Um, Generally, a partial differential equation is denoted in this form, right? A del square u by del x square plus b del square u by del x del y plus c del square u by del y square plus uh, d del u by del x plus e del u by del y plus f u is equal to g. So basically, it's a second order partial differential equation. So it will have all kinds of second order derivative terms, all kinds of first order derivative terms, partial derivative terms, and just the function without a derivative, the basic function, and some function on the right hand side. So this is your general form. And what is elliptic partial differential equation in this? An elliptic partial differential equation is basically when the discriminant delta, which is b square minus 4ac, is less than 0, then it's an elliptic PDE, right? This is what an elliptic PDE means. So now, uh, what we have to see is whether we can make these partial differential equations given in the question elliptic or not. So again, I'm not trying out all the options. I'll just select one. Say I'll choose the first option and solve it, and the rest are pretty straightforward and simple. So the first example is 5 del square u by del x square plus 16 eta del square u by del x del y minus 13 del square u by del y square is equal to 0. This is your first example. Uh, Here we can very easily identify that this is B, this is A, and this is C. So B square minus 4AC is equal to 256 eta square minus 4 into 5 into minus 13. This is equal to what? 256 eta square minus 20 into 20, 13 to 260. So this is, let me check for sure. Okay, B square. This is C. 4 into A. Okay, so thing is, I can see here that this can be clearly made elliptic, right? So suppose if I say 256 eta square has to be less than 260. So I can make an appropriate choice of eta square due to which this inequality can be satisfied, and I am able to make this elliptic. But apparently, um, okay, just give me a moment to check whether I'm making mistake anywhere. Um, C. Okay, the only mistake that I'm making is this. Right, sorry, my bad. So this is 260, but this is 256 eta square is less than minus 260. Sorry, my bad. So because there is a negative sign on the right hand side, of course we cannot, eta being real, I cannot have 256 eta square ever being a negative number, right? So for that simple reason, if eta is real, um, this PDE can never be elliptic. Yeah, so this is the answer. So first option is not valid. Um, it cannot be made elliptic even by a suitable choice of eta. There is no suitable choice of eta by which we can make the first PD elliptic. Let's try the second one. Let's see whether we get something or not. So similarly, for the second one, A is equal to 15 eta, B is equal to 18, C is equal to minus 20. So again, the same thing, B square minus 4AC is equal to 324 plus 16 to 20, 60 into 1200 eta has to be less than 0. So here, because eta is linear, the eta that comes in the equation is linear. So by a suitable choice of eta, you can actually make this equation elliptic. So that's the whole point here, because eta square we're getting, and because eta is real, this cannot ever happen, but this can happen. So basically, the second case seems to be correct, that you can make it elliptic, right? So this is how you're supposed to solve the other parts as well. This is very pretty straightforward. There's nothing complicated to be done here. Here, second question, just the framing is different, but the idea is still similar. Consider the following PDEs in which the parameter eta is real, and identify all PDEs that are necessarily hyperbolic. So for elliptic, b square minus 4ac is less than 0. Hyperbolic PDEs, b square minus 4ac is simply greater than 0. That's it. So now we have these four partial differential equations. Let's choose, say, randomly the third one, that are necessarily hyperbolic. So let's see what do we get. A is equal to 2 eta, B is equal to 10, C is equal to minus 8. So therefore, B square minus 4AC. I'm doing the third one. So for that, I've written A, B, and C. And B square minus 4AC for the third equation comes out to be 100 minus 4 into 2 eta into minus 8 is equal to 100 plus 64 eta greater than 0. So eta has to be greater than what, minus 100 by 64, which is pretty much okay. But the point being, what has been asked is the PD has to be necessarily hyperbolic. Here in this case, it's not going to be necessarily hyperbolic. Eta can be a number lesser than minus 100 by 64 as well. So there is no necessity as such. There is no necessity as such for the PD to be hyperbolic. So yeah, this does not necessitate. So cross, this one is not necessarily hyperbolic. It can be hyperbolic, but it's not necessarily hyperbolic. That is the difference. All right. So similarly, you can solve the other four options wherever there is some necessity, as in uh, eta square or something comes up, and you know that because eta is real, eta square is going to be positive, and the inequality is such that on the right hand side there is something negative, and eta square has to be greater than that. So for example, if you get something like eta square greater than minus 100 by 64, if this was the case in the other parts, I'm saying here we've already solved this. In the other parts, if this is the case somewhere, then clearly this is necessarily hyperbolic. So you have to find some case like that where it is necessary for uh, the equation to be hyperbolic. The one that we saw, it's not necessary. Okay, so that's the point. You can check the other parts. I'll move on to the third question. Again, third question is also very similar. Identify all PDs that are never parabolic. So for parabolic, b square minus 4ac has to be equal to 0. So it's the same drill again. You take an equation, write b square minus 4ac, and check whether you get a condition where it can never be 0, and there will be other conditions where it can be 0, it can not be 0 either way. So if it's dicey whether it can be 0 and cannot be 0, then they can be parabolic. But those that are never parabolic, there it can never be 0. So that is what you have to check. Okay, maybe I should take one example here. Uh, all right. So let's randomly take the third option. 15 del square u by del x square plus 13 eta del square u upon del x del y minus 14 del square u del y square is equal to 0. So in this case, a is equal to 15, b is equal to 13 eta, c is equal to minus 14, b square minus 4ac is equal to 2, sorry, this is 169 eta square minus 4 into 15 to minus 14, 9 eta square plus 60 into 14. 14, 3 is 42, 88, 40. So this is always necessarily greater than 0, right? Because eta is real, so eta square is going to be positive, and there is a positive number. So this is always going to be greater than 0. But for parabolic equation, we want this to be equal to 0. So in that case, we know that this can never be parabolic, never be parabolic PD. So hence, third is the correct option. Similarly, you can solve the other parts. Okay, the fourth one. Okay, what's the fourth question is? Mm, so reduce the following PDE. There's a partial differential equation given. I have to reduce it to its canonical form. I have to reduce the partial differential equation to its canonical form, right? So d square u by dx square minus 2 sin x d square u by dx dy minus cos square x del square u by del y square minus cos x del u by del y is equal to 0. Okay, so a is equal to 1, b is equal to minus 2. By the way, what is canonical form? So, sir mentioned in this lecture that um, a general second order PDE will have all the second order terms. It will have del square u by del x square, del square u by del y square, del square u by del x del y. Canonical form would be that you eliminate either the cross term or del square u by del x square and del square u by del y square. So basically, in canonical form, you will have either of these three kinds of terms. You can have del square u by del x square and del square u by del y square. You will have this set, or you will have del square u by del x del y only, and not the other two. So generally, partial differential equations of this form are much easier to solve. The ones where we have all three kinds of terms of the second order, that is more difficult to solve. So that is why you generally first reduce it to canonical form, and then we try to use very different techniques that we have to solve partial differential equations. So the first step is generally to reduce it to canonical form, and that is what we are doing through these problems. I think next three problems are like that. Okay, so this partial differential equation is given. A is equal to 1, b is equal to minus 2 sin x, c is equal to minus cos squared x, right? So b square minus 4ac again. B square minus 4ac is equal to 4 sine square x plus 4 cos square x is equal to 4. Just give me a moment. Hmm. So b square minus 4ac is 4, which is always greater than 0. So this is a hyperbolic PDE. Now, what do we do generally? dy by dx. The standard method is dy by dx is minus b plus minus b square minus 4ac by 2a, right? And we solve for dy by dx. We solve that differential equation ODE basically uh, to get our eta and zeta. So let's do this first. Minus b plus square root of b square minus 4ac by 2a. Let's do it simultaneously actually. Maybe I'll do that. Okay, so here it will be dy by dx is equal to minus b minus square root of You also have an overall negative sign outside, which I forgot to write down. Minus b minus b square minus 4ac divided by 2a. Okay, so what does it become in this case? It's um, b, which is minus 2 sine x minus square root of, which is 4. B square minus 4ac is a constant, right? Which is 4. Uh, Minus 2, I should write. The square root of 4 is 2. Yeah, and there is a minus sign there. Divided by 2 into a, which is 2. So hence this is minus of 1 plus sine x. Here dy by dx is equal to what? Same thing, minus 2 sine x plus 2 divided by 2. Therefore, this is 1 minus sine x. So here y is equal to minus x. I'm integrating basically because this is dy by dx. So now in the left one I'm integrating. Minus x minus integral of sine x will give me plus cos x, is it? The sign will change, right? Yes. Plus some constant c1. Here what does it become? X plus cos x plus c2. Therefore y plus x minus cos x is equal to c1. Y minus x minus cos x is equal to c2. So this we can take it as eta x comma y, sorry, zeta, and this we can take it eta x comma y. This, therefore zeta of x comma y is equal to y plus x minus cos x, and eta is equal to y minus x minus cos x. Okay, so once we found eta and zeta, then the next step generally is solving this, finding these new coefficients. So basically we have some original form of differential equation, say a del square u by del x square plus b del square u by del x del y plus c del square u by del y square plus d del u by del x plus e del u by del y plus f u is equal to g. So from here, when we convert to canonical form, we want to do it, convert it like this: del square u by del zeta square plus eta square plus b del square u by del zeta del eta plus c, sorry, capital B plus capital C del square u by del eta square plus capital D del u by del zeta plus capital E del u by del eta plus capital F into u is equal to capital G. So we are converting this particular form to this particular form. This is your canonical transformation. So we have to find these coefficients, capital A, B, C, etc. So there are standard. So sir has given these standard expressions, which I'm going to copy from sir's notes only. Okay. So capital A is small a into del psi by del x the whole square plus b del psi by del x. I'm saying sides, zeta, sorry, plus c del zeta by del phi the whole square. Del zeta by del x is equal to plus sin x. Del zeta by del y is equal to 1. Therefore, a is equal to, what is small a though? Small a is 1. 1 into sine square x plus b. What is b? B is minus 2 sin x. Minus 2 sin x del zeta by del x is sin x into 1 plus c. What is c? C is minus cos x square. Minus cos square x to 1. So this gives me what? Minus 1. Capital A 1 plus sin x. I'm making some silly mistakes. This is equal to 1 only. What does this give me? This gives me 1 plus sine square x plus 2 sin x minus 2 sin x is 2 sin square x minus cos square x. 1 minus sine square x minus cos square x is equal to 0. So therefore, capital A is equal to 0. What about capital B? Firstly, the expression for capital B is 2a del psi by del x del theta by del x plus b del psi by del x del eta by del y plus del psi by del y del eta by del x plus 2c del psi by del y del eta by del y is equal to 2 into a is 1 del psi by del x is sine x plus 1 del, what I want is now del eta. Del eta by del x is what? Minus 1 minus, sorry, minus 1 plus sine x del eta by del y is equal to 1 again. So here what is it? Del zeta by del x, del eta by del x. So minus 1 plus sine x, minus 1 plus sine x plus b, which is minus 2 cos x. Is that true? B is minus 2 sine x, sorry. Minus 2 sine x. D zeta by dx is sine of x plus 1. D eta by dy, which is 1, plus d zeta by dy is 1, d eta by dx is minus 1 plus sine x. plus 2c minus 2 cos square x minus 2 cos square x del zeta by del y del eta by del y again. Alright, so what this becomes is 2 into sine square x minus 1 sin x minus 1 sin x plus 1 sin square x minus 1 plus minus 4 sin square x minus 4 sin x. Hmm. So here I have 2 sin square x minus 4 sin square x. Okay, so this is minus 2 sin square x minus 2. This is just 1, not 2, right? Deta by dy is 1, so here also it's 1. So it's just 2. And this also is just like that, plus 2 sin x. Made a little bit of mess. Let me do this again. So 2 into sine square x minus 1 plus or plus, I'll take this inside, minus 2 sine square x minus 2 sine x. Same thing here, plus 2 sine x minus 2 sine square x. And here it's minus 2 cos square x. So this is minus 2 minus plus 2 sine square x. This gets cancelled. Minus 4 sine square x minus 2 cos square x. So this becomes minus 2 minus 2 minus 2 is minus 2. So this is equal to plus minus 4 is what I am left with. Capital B is minus 4. C is equal to what? A into by del x the whole square plus B into del eta by del x del eta by del y plus C del eta by del y whole square. This is equal to A is 1, del eta by del x is sine x minus 1 the whole square plus B is minus 2 sine x into del n by del x is sine x minus 1 into 1. C is minus cos square x into 1. C is minus cos square x, this is minus 2 sin x. D in d eta by dx, I'll just check. Eta by dx is minus 1 plus sin x minus 1. And d eta by dy is 1. That, yes, this I have written. This is equal to sin square x plus 1 minus 2 sin x minus 2 sin x minus 2 sin square x plus 2 sin x minus cos square x. So 1 minus 2 sin x plus 2 sin x gets cancelled. Minus sin square x minus cos square x, again 0, just like capital A. Just like capital in a very similar manner, this also becomes 0. What is d? D is a del square psi by del x square plus b del square psi by del x del y plus c del square psi by del y square plus d del psi by del x plus e del psi by del y. So del del by del x of del psi by del x. Del psi by del x we already know is 1 plus sin x. So this is equal to cos x. Del square eta by del square psi by del y square. This is going to be equal to 0. Yeah, this is going to be equal to 0. Del square psi by del x del y is also going to be 0, because del psi by del y we already know is just a constant, it's 1. So again, taking derivative with x gives me 0. So yeah, this is this. All right, so let's evaluate d. Capital D is a, which is 1 into del square psi by del x square, which is cos x, plus b into 0 plus c into 0 plus d and e. Sorry, d is equal to minus cos x. Sorry, e is minus cos x because it's del u by del y. So e is minus cos x and d is 0. So here also 0 into something plus e is minus cos x. E is minus cos x into del zeta by del y, which is 1. Capital D also comes out to be 0 apparently. Capital E. Now, capital E is A del square eta by del x square plus B del square eta by del x del y plus C del square eta by del y square plus D del eta by del x plus E del eta by del y. Same thing. Del square eta by del x square is sin x minus 1 it was. So this becomes cos x again. This also is cos x, and other terms are 0. These two, del square eta by del x del y is equal to del square eta by del y square is equal to 0. Okay, so 1 into cos x plus 0 plus 0 plus 1 plus 2 sin x minus 1 plus 2 sin x minus 1 plus 0 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 plus D is also 0 plus E into dou eta by dou y minus cos x 1 is also equal to 0. E is also equal to 0. Capital F is just small f, which is 0. Capital G is equal to small g, which is equal to 0. So this is my new partial differential equation. What is it? I just have B to be non-zero. Therefore, minus 4 del square U by del eta del zeta is 0. Therefore, U basically is a function of eta plus a function of zeta. This is what U is. Therefore, converting eta and zeta to their respective forms, usual f of eta is what? Y minus x minus cos x. Y minus x minus cos x plus g of y plus x minus cos x. Y minus x minus cos x, y plus x minus cos x. Y minus x minus cos x, y plus x minus cos x. Right? Minus, yes, this one. So this comes out to be the correct answer. I hope this problem was clear. It is a very straightforward method. All you have to do is always start with first check what is the discriminant. I cannot hear you clearly. Sanjeev, I could not hear your question very clearly. Can you repeat? Yeah, yeah. So I did explain that in the beginning itself. So what do we do is generally so we have three different kinds of second order derivative terms. So we have del square u by del x square, we have del square u by del y square, we have del square u by del x del y. And having all these three terms in the partial differential equation, the equation becomes very difficult to solve. So we have a lot of standardized techniques to solve partial differential equations. And generally, it becomes much more difficult to solve when we have all three kinds of second order terms. So canonical form means we generally, what we do is we should have only either we have del square u by del x square and del square u by del y square, both these will be in the equation, or we'll have just del square u by del x del y in the equation. The other two won't be there. So reducing your normal partial differential equation into a form where we have only these kinds of terms. Either we don't have a cross term or we only have cross term as the second order, highest second order term. Is that clear? We want either just the cross term or we want to eliminate the cross term. That is the whole point of canonical equation. So that is what we try to do. Here, what you see the canonical form, you just have the cross term. You don't have the other two terms, the diagonal terms that they call technically. So del square u by del x square and del square u by del y square, we have been able to avoid. And we finally found only del square u by del x del y form. So that is basically the idea behind reducing it to canonical form. Yeah. So yes, so this is what we ended up with. Solving this is not very hard. This is a very simple form. So we directly got the solution in this manner. This is a family of equations, of course. So we got the solution in this manner. Uh, but yeah, so generally we'll have to use different techniques to solve this part as well. This simple partial differential equation also. Okay, so this is the idea behind canonical forms. Okay, so the fifth question, reduce this PD to canonical form and solve it. Again, the same thing. You have to reduce this to canonical form. Uh, let's see. A is equal to y square, B is equal to minus 2xy, C is equal to x square, D, D is equal to minus y square by x, E is equal to minus x square by y, right? So B square minus 4AC is equal to what? 4x square y square minus 4x square y square is equal to 0. So this is what? A parabolic kind. Here we have a very specific way to reduce it to canonical form because b square minus 4ac becomes 0. So what do we have is dy by dx. Only one form we get is b by 2a, right? We don't have two different dy by dx equation. Here if you see, there are two dy by dx equations which we solved simultaneously. This was one where we had a plus sign. This was the second where we had a minus sign. So because any quadratic has two solutions. But here, because b square minus 4ac is equal to 0, we get only one solution, only b by 2a. dy by dx is b by 2a, which is equal to what? B is minus 2xy divided by 2a, 2y square is equal to minus minus x by y. So therefore, y square by 2 is equal to minus x square by 2 plus constant c1. So basically this is of the form x square plus y square is equal to some c1, and this is my. Now once I've determined what zeta is, we have to choose some form of eta. I have to choose some form of eta. How do I do that? We have to, well, there are a lot of possibilities, but they should basically give Jacobian to be non-zero. That's the only requirement. This is my zeta, so zeta is equal to x square plus y square. Now what is Jacobian? Jacobian is del eta by del x and del eta by del y, the determinant of this, right? So which is equal to del eta by del x, del eta by del y minus del eta by del y, del eta by del x. This is my Jacobian's form. So let's say I take eta to be equal to y just to try it out. So in that case, del eta by del x is equal to 0, del eta by del y is equal to 1, and del zeta by del x is equal to 2x, del zeta by del y is equal to 2y. So 2x del zeta by del x. del by del y 1 minus eta by del y is 2y del eta by del x 0. This gives me 2x. Okay, so what I did here was zeta I took as x square plus y square. Uh, Eta I took as some random function y. And when we try to evaluate the Jacobian, del zeta by del x 2x, del eta by del y is 1. Just give me a moment. Take this. हाँ भैया, हाँ हाँ बोलिए बोलिए, मेरा लेक्चर चल रहा है, कुछ अर्जेंट काम था। मैं ऑनलाइन लेक्चर ले रहा हूँ। हाँ हाँ, ओके ओके, 9 9 साढ़े 9 के बाद कॉल करता हूँ। हाँ बाय। Okay, so we can see that this Jacobian, yeah, I'm audible. So we can see that this Jacobian gives out a non-zero number. Let's check that again. Del y del eta by del x. 2y del eta by del x is 0. So this becomes 0. All I'm left with is 2x. Yeah, so this is also a valid function that can be used. So let's write them down both. This is equal to x square plus y square. Eta is equal to y. This is the choice of zeta and eta that we are using. All right, now again the same old machinery. Uh, Capital A, del eta by del x is equal to 2x, del zeta by del y is equal to 2y, del square by x square is equal to 2, del square by del square is also equal to 2. Same thing with del square eta by, sorry, del eta by del x is equal to 0, del eta by del y is equal to 1, del square eta by del x square is equal to 0, del square eta by del y square is also equal to 0. Del square zeta by del x del y is equal to 0, del square eta by del x del y is also equal to 0. Alright, so now let's start, and we know a, b, c and everything. A was, yeah, these are the functions. Alright, so capital A is what? Small a into uh, plus b into del xi by del x del xi by del y plus c into del xi by del y the whole square. So all I want is ABC. Y square is 2xy x square. Y square is 2xy x square. And del xi by del x the whole square, which is 4x square. B into 2x into 2y plus c into x square del 4y square. So this becomes equal to what? 4x square y square minus 8x square y square plus 4x square y square. What is 0? So capital A comes out to be 0. Capital B comes out to be what? uh, 2a into del xi by del x del eta by del x plus b del xi by del x del eta by del y plus del xi by del y del eta by del x plus 2c del xi by del y del eta by del y is equal to 2y square del xi by del x 2x del eta by del x 0 plus small b is minus 2xy minus 2xy del psi by del x is again 2x del eta by del y 1 plus del xi by del y which is again 2y del eta by del x is 0 plus 2 into c x squared del zeta by del y is 2y del eta by del y is 1 2 sorry 4x y square. Okay, this is eta by del x the whole square plus b into del eta by del x del eta by del y plus c into del eta by del y whole square. And what does this become equal to? A is again y square del eta by del x is 0, right? Yes, this is 0 plus b, which is minus 2xy minus 2xy 0 plus c del eta by del y the whole square, which is 1 square, which is 1. So therefore what we get is capital C is equal to just x squared. Mhm. All right. I'll keep these constants here because then they come out handy when I'm trying to write these equations out. Um, D is what? A into del square psi by del x square plus B into del square psi by del x del y plus C del square psi by del y square plus D into del square, sorry, del psi by del x plus E into del psi by del y. This is my D, capital D. So A is, I've written it here, A, y square into del square psi by del x square is giving me 2, right? 5, yeah. Plus B minus 2xy 0 plus C is x square and also, this is also 2 plus D minus y square by x into del psi by del x is 2x plus E. E is what? Minus x square y into 2y. Del psi by del y is 2y. So yeah, there is 2y square, 2x square, minus 2 x gets cancelled, y gets cancelled, minus 2x square minus 2y square. This is also, this is equal to 0. Capital E, A into del square eta by del x square plus B into del square eta by del x del y plus C into del square eta by del sorry, by del y square plus D into del eta by del eta by del x E into del eta by del y. Yes, this is it. Now again I use y square. Del square eta by del x square is going to be 0. Del square eta by del x square. Eta is just y, right? Absolutely. So this is 0 plus minus 2xy into 0 again, plus c into 0. I don't care what that number is. D is minus y square by x into del eta by del x 0 plus E is minus x square by y del eta by del y is 1. D into del eta by del x, because eta is y, yeah, 0. E into 1 and this is 0. This is everything else is 0, just this. So just this comes out to be minus x square by y, capital E. Capital F is equal to capital G is equal to 0, because that's not present as a term. So what does this imply? This implies C is what? X square del square u by del eta square. E and there is F and there is G. G is the constant function on the right. Everything is 0, so this is 0. This is the PD that I obtain. Um, Now x cannot be equal to 0, of course. Del square u by del eta square minus 1 by y del u by del eta is equal to 0. Del by del y of del u by del y is equal to 1 by y del u by del y. Let's say del u by del y is some other function f. So therefore, what does this become? Del f by del y is equal to f by y is equal to f. Yeah, so del f by del y is equal to f by y. Yes. So how do we solve it? This is simply ln f is equal to ln y plus c. So therefore, basically, this is f by y is equal to some constant c1 del u by del y is equal to some c1 into y. So u is equal to some c1 y square. So f by y is f by y is c1. That does make sense, right? I take it to the left. Ln f minus ln y is equal to c. So f by y is c1, um, which is del u by del y um, is equal to c1 into y. It's c1 into y square plus plus this is some function of, sorry, here itself I can do this, right? So y into g of zeta. So what does this become? This becomes actually, why can't I can simply accommodate this inside? So this is simply g of zeta only, nothing else. G of zeta. So what do I have? Y into g of zeta. This has a constant inside of it. U becomes y square g of zeta plus h of zeta. Okay, so I eventually end up getting the answer y square g of x square plus y square plus h of x square plus y square. This is u. Are those options here? Y square f of x square is g of x square y square. I do get this one. So maybe you can check with some other form. Uh, maybe take eta. We've taken eta as y. Maybe you can take eta as x or something else, and maybe check whether that also gives you something. Mm, yeah, and that would give you the other. That would give you another option. Okay, again, this is the next question. Again, is about reducing it to canonical form only, and we've already done two parts. Only the difference here is that how do we choose eta and zeta? Maybe I'll do till that part only, and then leave the rest for you to do, because this is taking quite some time and we'll not be able to solve the other questions after this. So again, transform to PDE. Here A is equal to 1, B is equal to 2, C is equal to 4, D is equal to 2, E is equal to 3. So B square minus 4 AC is equal to 4 minus 4 into 4 is equal to minus 12, which is less than 0. So this is elliptic very clearly. So in this case, dy by dx is equal to b, which is 2, 4 minus 4 ac, 16. So this is square root of 12 minus 12 actually. Square root of minus 12 divided by 2, and dy by dx is equal to 2 plus square root of minus 12 by 2. Square root of minus 12 is just 2 root 3 I, 2I root 3, uh, which gets cancelled. So this is equal to 1 minus I root 3, and this is dy by dx. Dy by dx is equal to 1 plus I root 3. This is what we end up with. These are the two forms that we get. So therefore, y is equal to y minus of 1 minus I root 3 x is equal to some c1, and y minus of 1 plus I root 3 x is some c2. This is your c1 and c2. Yes. So your eta is y minus 1 minus I root 3 x, and sorry, zeta, and eta is y minus 1 plus I root 3. I'm audible, right? Yeah. So eta and zeta are such functions that you have imaginary numbers also inside of them. So what do we do to convert this? The method prescribed in the lectures is, we define two variables alpha and beta. Alpha is zeta plus eta by 2. That gives you what? Zeta plus eta by 2. So y remains the same, minus 1, this remains the same. So y minus x. This apparently becomes y minus x, right? And yeah, okay. And then this beta also, which is minus uh, eta by 2i. So what does this give you? This cancels out. Y gets cancelled, 1 gets cancelled. Only I root 3 minus plus I root 3. So it what it gives me is root 3 x is what remains. All that remains is just root 3x. Alpha is y minus x and beta is root 3x. So these are my two equation. These are my two new variables using which I'll write the canonical PD, canonical form of the PD. So again, exactly that. Just the difference would be that instead of zeta and eta, you'll be replacing everything by alpha and beta. That's it. Or maybe you can call these your new zeta and eta and solve further. Rather than complicating it further, you can just call this zeta and eta and the whole mechanism, capital A, capital B, all of that you did previously. That's all you're supposed to do. And find coefficients. And finally, you will find the canonical form and you can solve it. So the same mechanism, just that this is the only difference that for elliptic equation, your eta and zeta, the way we defined eta and zeta till now, you will find them to be imaginary. So you take a linear combination of them. You take a linear perpendicular combination of them and um, such that they become real. And it's easier to work with real variables. So that's all we do. And these are your new eta and zeta, which are real now, and they're still their Jacobian will still give you non-zero value, and then you evaluate further, you calculate further. So yeah, that's the only difference, and you should get your answer what's asked for in the question. So I hope that's clear, and we will not spend any more time here. We'll move forward. Uh, so now solve this Laplace equation. Okay. So we have this Laplace equation and it satisfies the boundary condition. This is your Dirichlet boundary condition because you have been given basically on all the boundaries you have been given values of the function directly. If you would have been given the derivative value of the function, the value of the derivative of the function, in that case the boundary condition will be called Neumann boundary condition. Here in this case we are given the exact value of the function at the boundaries or the functional form, not if the exact value, the functional form. But what you're getting is the value of the function itself at the boundary and not its derivative. So that's why these are Dirichlet boundary conditions. So what you're asked to do is solve this Laplace equation del square u is equal to 0, um, where you have defined the boundary of x and y, where x is going from 0 to 1. So this is a box basically. It's a square box. X is going from 0 to 1, y is going from 0 to 1, u of x comma 1. So at this boundary, u of x comma 1. So this is basically my x and this is my y. So u of x comma 1 is this edge, u is equal to x minus x square on this edge. On the left edge, where u of 0 comma y, this is 0, u of 1 comma y is 0, and u of x comma 0 is 0. So on all these three edges, no, let this stay, erase this. So on these three edges, the value is 0. On the fourth edge, this is x square minus y square. I'll rather not draw the coordinate system here. I'll draw the coordinate system here, x and y, and this is my origin. This is x equal to 1, this is y equal to 1. Yes, so this is the system that we are looking at, and this satisfies the Laplace equation, whatever the variable or the function that we are trying to look at. that function satisfies Laplace equation and the boundary conditions are given. So now you want to solve it for all the values inside this boundary. Okay, so as we've seen in the lectures, there are generally three kinds of cases that emerge. So for x and y, we are doing the variable separation method. So capital X could be of the form alpha sine px plus beta cos px, where p is something that we'll figure out, and y can be of the form uh, a e raised to power py plus b e raised to power minus py. This is one possible solution. The second one is we'll swap the functions between x and y. So x will have alpha e raised to power py plus beta e raised to power minus py, and y will have a e raised to power a sine px plus b cos px. So swapping the function. And the third kind of solution is that it will be just basically p will be 0. So it will be just a straight line in x and y both. But that we know will not work in this case because a straight line will have some slope and keep on going in one direction. So if you're starting with 0 at one value at one end, it can't stay 0 at the second end. So it's a suppose x is uh, ax plus b. Capital X function is ax plus b of this form. At x equal to 0, the value can be 0, but at x equal to 1 also the value cannot be 0. It cannot go to the same value again if it's a straight line. So, and similarly in the y direction also that cannot happen. So this solution at least we can eliminate. The p equal to 0 solution is very easily eliminated. Now, in the x direction, whether it can be sin px and cos px form, how will you determine that? Clearly, in the x direction, it starts at 0 and it goes back to 0. Even the exponential function, it starts at some value and it has one particular slope. It keeps on increasing. So, because in the x direction, I start from 0 and go back to 0, I will take the sinusoidal form in the x direction and I will take the exponential form in the y direction. Let's start with that basic premise and see whether this fits or not. So I hope you understood what I'm trying to say. The form of u that I will assume, and always in the Fourier series form, n alpha n sine px plus beta n cos px a n e raised to power py plus b n e raised to power minus py. So this is the form of solution that we can assume. Mm, Let me just. Okay, fine. So now uh, we have to implement the boundary conditions. So u of 0 comma y is 0 comma y is equal to 0. So in that case, beta n comes out to be 0, right? Because x is 0, so alpha this term becomes 0, but this still remains beta n cos px into a n e power py and everything. So beta n remains. So beta n has to go to 0 because the right hand side is 0. So beta n becomes equal to 0. This is what we get. So u becomes what? Alpha n sine px an e power py plus bn e power minus py. Actually now because there are already coefficients inside, I can absorb alpha n into an and bn. So I don't need to write alpha n separately. So this just becomes sine px. Okay, so that's that. Mm, Now another boundary condition, which is u of 1 comma y. U of 1 comma y is also 0. U of 1 comma y is equal to sum over n sine p, because x is equal to 1 and this is whatever, this is equal to 0. This function is non-zero at many values, but this has to go to 0 always. at this value. So sine p is equal to 0. Therefore, p is equal to n pi. So I am putting x equal to 1. So when I put x equal to 1, so sine p into, there is this function of y which can take any value, because y I am keeping as a variable, right? Yeah. So that can take any value. So obviously sine p only has to go to 0, because y is a variable and can change. A n and b n are non-zero and y is a variable. Till now we assumed a n and b n are non-zero and y is a variable. So in that case, only sine p can go to 0. Sine p has to go to 0 necessarily. So that is why p has to be n pi form, but n we have already used as a variable, so maybe I'll use some other number, some other variable, m pi. P is some n pi. Basically, m is an integer, so p is some integer into pi, right? That's when sine is 0, only at integer value of pi. So now this becomes some over n sine of m pi. Let me see. I think I'm getting confused. This is all okay. Uh, no, I think I should not have started with this actually. So this is alpha, beta, A, B. My bad. It doesn't necessarily start with this summation thing. Yes, A, B. So this is I'm writing just as a variable separated form, a general solution. Uh, so here again I can remove this n. So this is some n pi. Now when I'm writing the final form u x comma y, I have sine n pi some integer into a e power py plus b e raised to power minus py. This is the form of function that I have. Okay, but as we know that this form of function need not necessarily satisfy the boundary condition at y equal to 1, because it's a very specific function. And here what we have is sinusoidals and exponentials. So to do that, we'll have to take a linear combination of all the sine n pi's. Of course, we know that the solution of differential equation, if one is a particular solution, so all like if sine n pi, we know that n is any integer. So what we'll do is we'll use that. Okay, so what I'm trying to say is if I know one solution y1, so if y1 is a solution of a particular differential equation, y2 is also a solution of particular differential equation, then alpha y1 plus beta y2 is a solution, is also a solution of the same differential equation, right? So that's what I'm trying to say. I know that sine pi into this function is a solution. Sine 2 pi, sorry, x cannot go away. Pi x into this, 2 pi x into this is also a solution. Sine 3 pi x into this is also a solution. So what I'm saying is that I'll take a linear combination of all these possibilities and write it in terms of a Fourier sine series with the right hand side staying intact, the exponential part staying intact. I will write this as a Fourier sine series, and by doing that, by writing it as a Fourier sine series, I will be able to simulate any boundary condition, any function on the boundary I can get by writing as a Fourier sine series. Just sine pi x or sine 2 pi x individually will not be able to give me that boundary condition, but this can. Okay, so that's one thing. So that's why at this step we generally write as Fourier sine series. I, as a method, I just started doing it, but we should generally understand it properly. So, okay, by the way, so p is just n pi. So here also I'll be writing it as n pi only. a e raised to power n pi y minus n pi y. All right. One more boundary condition I can already implement at y equal to 0. At y equal to 0, I have 0. So, and x can be anything. So, is equal to, let's do this, u of x comma 1, sorry, 0. U of x comma 0 is given, right? U of x comma 0 is 0 is equal to sine n pi x into a plus b is equal to 0. Again, x is a variable, n pi, we know n is not equal to 0. So sine n pi x is not necessarily 0. It can be any number. So a plus b has to be 0 again. So a is equal to minus b. So this is what we end up getting. So therefore, u of x comma y is equal to sine n pi x sum a e raised to power n pi y. Wait, am I doing this correctly or not? Y I put as 0, right? Minus a e raised to power minus n pi y. I think this is fine. This seems pretty much fine. So therefore, this is the form n pi x. A I'm taking outside, and e raised to power some x minus e raised to power minus x. So I'll take 2 common outside, and this becomes sine h n pi y. Okay. Now this is just one particular kind of a solution. I can have any n here, right? That's what we just said, that any n is a solution. So that's why linear combination of all the n's is also a solution. So a general form of u of x comma y actually should be sum over n to a n. I'll actually even remove 2 from here. Let's just have a n sine n pi x sine h n pi y. Now the final boundary condition that we have, which will give me an, the form of an, is u of x comma 1, u of x comma 1, right? Y is 1. U of x comma 1 is equal to sum over n an sine n pi x sine h n pi. This is equal to what? X minus x squared. X minus x squared. So this is the whole reason why we wrote it as a Fourier sine series, because the right hand side is a function like x minus x squared. So that cannot be interpolated by just one sine function or one sin h function. It has to be interpolated by this whole linear combination. Okay. Uh, this sin h n pi is a constant. This Fourier sine series should give me this function on the right hand side. So we know how exactly to go about solving this. Um, these coefficients are given by how what an sine, sorry, an sine h n pi. This is the coefficient. This entire thing is the coefficient is equal to, how do we get the coefficient? Uh, 2 by a. A is that interval, uh, which is 0 to 1 only in this case. Yeah, 0 to 1, uh, x minus x square into sine n pi x dx. Sine of n pi x dx. This integral we have to evaluate, and this will give me the coefficient. So an sine h of n pi is equal to 2 x sine n pi x dx minus integral to x square sine of n pi x dx. 0 to 1, 0 to 1. Hmm. So this will have to be done using integration by parts. So I'm just solving the first part right now. 2 integral x dx. What's the integral by part thing here? Um, I'll integrate this. Yeah, so v and du. So we go d, yes. So integral minus cos n pi x divided by n pi 0 to 1 minus integral of 2 x is differentiated. This is minus cos n pi x by n pi and this dx 0 to 1. This is the integral. Okay, so this is equal to cos n pi 2 into 1 into minus cos of n pi divided by n pi. The second value is going to be 0 minus minus plus 2 cos n pi x again, that goes to positive sine n pi x divided by n square pi square is from 0 to 1. N pi and 0 both become 0, so this is 0. So the value is minus 2 cos of n pi divided by n pi. Yes, this is the first one. Now the second one. I'll not, I'll ignore the minus sign for now, which we'll take in later. I'll ignore the 2 right now. X square sine n pi x dx. Okay, so again the same drill. Um, x square minus cos n pi x divided by n pi 0 to 1 minus integral 2x minus cos n pi x by n pi dx. Hmm. So here when I put 1 again, so I get minus cos n pi divided by n pi. 0 gives me 0, but 1 gives me this again. Um, Minus 2, so it's 2x, but this is cos n pi x. There's a difference. Minus 2 upon n pi. Actually, I can remove this outside. Plus 2 by n pi integral x cos n pi x, which makes this integral of cos, which is sine n pi x divided by n pi into x 0 to 1 minus 2 by n pi integral sine n pi x divided by n pi dx. This goes to 0. So 1 and 0 both will give me 0. But minus cos n pi divided by n pi minus 2 by n pi n square pi square integral this. Sine का is minus cos n pi x just n pi 0 to 1. So this is minus cos n pi divided by n pi um, plus 2 cos n pi divided by n cube pi cube just plus and minus 2 divided by n cube pi cube. Right, so this is what we get. By the way, cos n pi is equal to minus 1 raised to power n. So because 2 pi will give me 1, just cos pi will give me minus 1. So cos pi is minus 1 power n. So this becomes minus 2 minus 1 raised to power n divided by n pi. And here I have not taken the negative sign and 2 both. So now when I include both the negative sign and 2, so minus 2 into this minus of minus 1 raised to power n upon n pi plus 2 into minus 1 raised to power n divided by n cube pi cube minus 2 by n cube pi cube. And I'll write this term as well, minus 2 minus 1 raised to power n divided by n pi minus 2 minus 1 raised to power n. So this gets cancelled. Okay, minus 4 minus 1 raised to power n divided by n cube pi cube plus 4 divided by n cube pi cube. So this is what the integral gives us, and this is equal to a n sine of n sine h of n pi. So therefore a n is equal to 4 divided by n cube pi cube sine h n pi 1 minus minus 1 raised to power n. This is my a n. I might have missed a 2 or something somewhere. N cube pi cube sine h. N cube pi cube sine h is what I am getting already. But there is same options with 8 and 16. So I'll have to be careful with the number. Hmm. Okay, but the thing is, acha, so 2k plus 1. Okay. So when n is even, when n is even, basically is equal to 2k, an is equal to 0, and when n is equal to odd, which is 2k plus 1, an is equal to 8 upon this 2k plus 1 the whole cube pi cube sine h 2k plus 1 pi. This is my an. Hence, 8 all option should be the correct answer. This one. And everywhere else, sine h 2k plus 1 pi y pi x. Yeah. So this has to be the correct answer. Yeah. Yeah. Tell me. You missed what point? Can you? U of 1 comma y is equal to 0, right? So first what we did was u of 0 comma y is equal to 0, right? That's the first boundary condition we used. So in that case, um, alpha goes away. Yeah, u of, no, I'm saying u of 0 comma y first. So for u of 0 comma y, when I'm putting x equal to 0, what I have is, you can look at the screen here in this case, beta cos of 0 into this function, which is basically beta into the whole function. This is equal to 0, right? Is that clear? Yes. So because of this, I come to know that beta is equal to 0, so cos goes away. Sorry, that's what I'm saying. For that, you need a cos term. If there was a cos term, we could have done something. But first boundary condition, u of 0 comma y, for that to be 0, cos cannot exist. Cos has to go away. The cos term has to go away, which is why I'm mentioning u of 0 comma y first. So there are four boundary conditions. I am starting with say u of 0 comma y. Okay. So u of 0 comma y means I'm putting x equal to 0. In that case, this being my original function, alpha sine px becomes 0, but beta cos px becomes beta when I put x equal to 0. So beta into the y function, into the function of y, has to be equal to 0. Now the function of y cannot become 0. That is a variable function. So beta has to go to 0. So when I take beta equal to 0, then cos px does not exist anymore. So further, when I'm putting other boundary conditions, I don't have to consider cos px. I only have to take sin px. Got it? Okay, okay, fine. All right. So this is problem number 7. Now, if we see problem number 8, three sides of a square plate of side 10 centimeter are held at 0 degrees Celsius and the fourth side is maintained 100. Find the temperature at the center of the plate. This is again going to be absolutely the same question. It would be even simpler because it won't be simpler actually, but instead of x square minus x that we had here, we had x square minus x as the function here, x minus x square. We'll have some constant number. So we'll write a Fourier sine series and the right hand side will be some constant number. And that's how here there'll be some constant number and that's how we'll find the coefficients. So only the coefficient finding procedure of the function there is going to change. Nothing else is changing. Everything else is same. Three sides maintained at 0, fourth side at 100. So exactly the same. Ninth question, three sides of a square plate are held at 100, fourth side at 0. Find the temperature at the center of the plate. Again the same thing. Absolutely the same thing. here, but there might be a difference in the initial function that you choose. 3 sides at 100 means um, we might have to take the cos function. So that you'll have to see. Here maybe the sine function will not be maintained. We'll have to take the cos function. But again, rest of the things are absolutely the same. You just start with the basic form that we started with, implement the boundary conditions, and you will see what form works. 10th one is a semi-infinite rectangular metal strip. Semi-infinite, okay. This is again absolutely similar. All of these problems, even if it's semi-infinite, even in that case, the exponential functions is something that you have to play with. The exponential negative e power minus py, whatever we had, that will survive. E power positive py will go to zero because at infinite distance, that function will shoot up. So we cannot have that function. So very similar problems here. Maybe I'll just take a look at this problem. Just give me a moment. You'll try? Okay. But just a moment, just a moment. This is my 10th problem. We'll just see this. The other problems are direct constant boundaries. So there is nothing to worry about. That's a very straightforward thing. Just for this, I'll see whether there's some hint necessary. So x and y is pi. X is restricted between 0 and pi. So this is my semi-infinite sheet. This is it. X equal to 0, x equal to pi, but in y it's infinite. In y its length is infinite. Right. So capital X, and what are the boundary conditions? Temperature of the bottom edge is maintained at T, x is cos x, while the other three edges are fixed at 0. So x function we'll take as a cos px plus b sin px. And the y function we'll take as alpha e power px plus beta e power minus px, while the other three edges are fixed at 0. Okay, so u is equal to this combination, right? A cos px plus b sin px multiplied by alpha e power px plus beta e power minus px. All right, so u of 0 comma y is what? This is equal to 0, and u of pi comma y is also equal to 0. U of x comma infinity is also 0, just that u of x comma 0 is equal to cos x. Yes, that's the bottom edge. So this is cos x, this is 0, this is 0, and at infinite also it's 0. So this is what we want to ensure. All of these boundary conditions will implement individually. So u of 0 comma y is equal to a cos px will give me 1. So a plus sin px will give me 0, and this is a function of y. So again a has to go to 0. just like we discussed right now. U of pi comma y also has to be 0. Uh, so therefore, b sine p pi has to be equal to 0 because the other y function does not really care, does not matter. So p has to be an integer. P has to belong to integer. I don't know. Probably you write it like this only. Z. P belongs to an integer. All right. Next, u of x comma infinity is equal to b sine px into e power minus px goes to 0. So this is 0 plus alpha. E power px actually shoots up. So we cannot have alpha. The alpha term cannot exist because otherwise if alpha term exists then it will shoot up. This is not x. I'm really sorry. This is y. Y. So yeah, that's what I'm saying. Beta e power minus py goes to 0 when y goes to infinity, but alpha e power py actually shoots up when y goes to infinity. So we cannot have that term. So because of this boundary condition, alpha is equal to 0 is something we get already. So now what is the form of u? The form that we get of u is some constant a, let's call it an, sine n x uh, e raised to power minus, we said p belongs to integer, right? E power minus ny. This is the form of u that we get. And now we've been told that u of x comma 0 is cos x. So basically sum over an sine nx has to be equal to cos x. Fourier sine series giving you a cos. So this is what you will solve for. So here you can simply find the coefficients corresponding to this function cos x and you proceed similarly. That's what all you have to do. It's just this. You start with this basic form for any boundary function that you want to interpolate. You have to do a Fourier sine series. That's it. It is as simple as that. The Laplace equation problems are just that. So yeah, let's end it here. Uh, if you have any doubts, you can ask. Yeah. Yes. 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 Lecture 8 will be uploaded soon. Yeah. Okay. Anything else? You're welcome. All right. Thank you. Bye.